Question 13. Two coherent wave sources are positioned at points A and B. Each source emits waves of the same frequency and constant amplitude. The waves travel through a uniform medium and meet at point D by following the paths shown in the diagram. The distance traveled by the wave from A to D is 72 centimeters, while the distance traveled by the wave from B to D is 90 centimeters. The wavelength of the waves in this medium is 4.0 centimeters. At point D, the two waves are observed to arrive exactly in antiphase. Which of the following gives the phase difference between the waves at the instant they leave points A and B? This question tests our understanding of phase difference and how path difference affects superposition. What do we know? We know that the path difference between two waves is the difference in the distance traveled by the waves to reach a particular point. Phase difference is related to path difference by the equation the phase difference phi equals 2 pi over lambda times the path difference delta x. This is when the phase is in radians, otherwise 360 degrees is used in place of 2 pi. We also know that waves that are in antiphase have a phase difference of pi radians, which is equivalent to 180 degrees. Finally, the total phase difference at a point is the sum of two things: the initial phase difference between the sources and the additional phase difference caused by the path difference. Now let's think through the solution step by step. First, we calculate the path difference between the two waves. The path difference is the distance traveled by the wave from B to D minus the distance traveled by the wave from A to D. So the path difference equals 90 centimeters minus 72 centimeters. This gives a path difference of 18 centimeters. Next, we note the wavelength of the waves in the medium. The wavelength is 4.0 centimeters. Now we determine the phase difference caused by this path difference. The phase difference produced by a path difference is given by 360 degrees divided by the wavelength multiplied by the path difference. Substituting the values, we get 360 degrees divided by 4 multiplied by 18. So the phase difference caused by the path difference alone is 1,620 degrees. However, phase differences repeat every 360 degrees, so we can subtract multiples of 360 to find an equivalent smaller angle. This smallest equivalent angle would also be less than 180 degrees, as the total phase difference at point D was 180 degrees for antiphase. So we subtract 4 times 360 degrees from 1,620 degrees. This gives 180 degrees. So the phase difference caused by the path difference is effectively 180 degrees. Now let us consider the total phase difference at point D. The total phase difference equals the initial phase difference between the sources plus the phase difference produced by the path difference. We are told that the waves arrive at point D in antiphase. Antiphase corresponds to a total phase difference of 180 degrees. So we can write 180 degrees equals the initial phase difference plus 180 degrees. Rearranging this equation gives the initial phase difference equals 180 degrees minus 180 degrees. This gives 0 degrees. So the waves must leave sources A and B with an initial phase difference of 0 degrees. In other words, the sources start in phase. This is our final answer. What did we do? We first calculated the path difference between the two waves, using the distances traveled from A and B to point D. Then we converted that path difference into a phase difference, using the relationship between wavelength and phase. After that, we used the idea that the total phase difference at the observation point is the sum of the initial phase difference and the phase difference caused by the path difference. Since the waves arrive in antiphase at point D, the total phase difference must be 180 degrees. Solving this allowed us to determine that the initial phase difference between the sources must be 0 degrees. Now let's address a common misconception. Students often think that if waves arrive in anti-phase, then the sources must have started with an initial phase difference of 180 degrees. But this ignores the effect of path difference. Even if two sources start perfectly in phase, the difference in the distances traveled by the waves can introduce a phase shift that causes the waves to arrive in antiphase at the observation point. Let's summarize the key takeaways. The path difference contributes a phase difference given by the relation phase difference equals 360 degrees multiplied by the path difference divided by the wavelength. The total phase difference at the observation point is the sum of the initial phase difference and the phase difference caused by the path difference. And finally, a phase difference of 180 degrees plus or minus any multiple of 360 degrees still represents antiphase. Values such as 540 degrees or negative 180 degrees are therefore also valid antiphase conditions.